Om Shri Sai Ram. Welcome to the fifth session of this chapter, Force and Laws of Motion. Having studied about Newton's third law of motion in the last chapter, in this session we will be talking about the application of the Newton's third law of motion, which we call as law of conservation of momentum. So before going into the law of conservation of momentum, we need to get familiar with some terms. So let us go and look at the terms and study about it. So systems. So what are this system and how many kinds of systems are there? Okay, in physics we will come across various kinds of systems and you will get more familiar in your class 11 in the chapter called thermodynamics. So for the law of conservation of momentum, we will be just dealing with the system of bodies. Before getting into the system of bodies, we have to just introduce to you this how many kinds of systems are there. Okay. So we have three kinds of systems. So to make it easy, we have taken in the same slide three different kinds of system in three boxes. So it does not mean that each box, this box represent open system, is the system will be open in a box. So it represents each system. So one is open system, the second one is closed system, the third one is isolated system, which is most important for our understanding in the law of conservation of momentum. Now let us talk about open system. We have two arrows here. So what does that represent? Red arrow represent exchange of energy with the surroundings, and blue arrow represents exchange of matter with the surroundings. When and where, as and when you find the arrow in the system, that means it has the independence, it has the liberty to exchange the energy or the matter with the surroundings. So what does the open system do? Open system is a kind of system which can exchange both the energy and matter with the surroundings. For example, if you take the hot boiling water in a vessel which is open with an open lid, what you can see? You can see the water vapor. Because it is boiling water, the water vapor content escapes out from the vessel, right? That means it is a matter. Water vapor is nothing but the matter content of the water. So matter is being exchanged with the surroundings. And also, if you keep your hands close to the walls of the vessel, you will find the heat, right? That means the heat of the water, the hotness of the water, to be precise, the heat energy which is being provided to the water is being dissipated through the walls of the container. That means heat energy is also exchanged with the surroundings. After some time, you can see that the water gets cool because all the heat energy in the water will get dissipated to the surroundings, right? So this kind of system is called as open system, where you can exchange the matter content and also the energy content of the water which is inside the vessel. All right. Now what is closed system? Closed system is nothing but when you shut down the exchange of matter content in an open system, it becomes closed system. That means it has only the independence of exchanging the energy. Now when you come to isolated system, what happens? You cannot exchange either matter and also the energy. So to be precise, you cannot have any external agency disturbing that system. So it cannot be disturbed what is inside the system. If any object or anything is inside the system, that cannot be disturbed by the surroundings. All right. So this is isolated system. Now we'll study the system of bodies which is being isolated. What is that? For example, you have body A, body B, and also body C. Now our system of interest, our area of interest to study the behavior of body A and B. So what you will do, we'll have the imaginary boundary in our mind to make the system of object A and object B. Now our system is what? AB. Our system, the objects in our system is AB, and C will be the external object of the system. It is not the part of the system. Our area of interest is A and B. So there may be forces between A and B, right? A can exert a force on B, B can exert a force on A. So when the forces are being exerted by the objects inside the system, okay, when these objects which are inside the system exert force on each other, those kind of forces we call as internal forces. We call as internal forces. If an external agency which is not the part of system is acting force on the system in any way, if C is exerting force on the A or B, that we call as external force, because C is not the part of system, right? Any force which is being exerted on the system of A and B we call as external forces. Any force which is between A, B, right? Any force which is in the objects of our system, in between the objects of our system, that we call as internal forces. So in an isolated system, to define an isolated system, what we need, what is the condition? The condition is your force external on the system should be equal to 0. External force on the system, if it is 0, we can call it as isolated system. Alright, this is very important for the concept which you are studying in the law of conservation of linear momentum. So before we go to the conservation of linear momentum, let us recap the concept of what is linear momentum. Alright, so what is linear momentum? Linear momentum is the measure of quantity of motion. It is a measure of quantity of motion possessed by a moving body, right, which I have already studied. So linear momentum is the product of mass of the body and its velocity. It is a product of mass of the body and the velocity. So it is represented by the letter P, we have already studied, which is m, and product of mass into body means what? When m is the mass, v is the velocity, it will be mv. And is it a scalar or vector? Because velocity is a vector here, your linear momentum is also a vector quantity. In which direction? In the direction of the velocity. So you will have the direction of momentum in the direction of your velocity. Okay. So and this is a product involving a scalar. A mass is always a scalar. It does not have any direction. It has only the value which is called its magnitude, and a vector v. Alright. This is about linear momentum. Some more points about linear momentum is a vector quantity, which I have already discussed now, and it has the same direction as the direction of the velocity of the body. So change in momentum. If the momentum is changing, you are acting, an external force is being acted on the system. But how do you measure the change in momentum? So some final momentum minus the initial momentum, right? That is what given here. So change in momentum is always calculated as the final momentum, how much momentum it acquired or lost after some time, minus the initial momentum where it started with. When you say about something has changed, it means the final quantity minus initial quantity, right? So that's where final momentum minus initial momentum, that is regarded as delta P, that is change in momentum. Delta is called as change. Change in what? Momentum. P is momentum. Change in momentum is mvf. This is what? This is final velocity. Final velocity. And this is your initial velocity, which it started with. Velocity. So as the momentum is a vector, vector subtraction must be used in finding the change in momentum. So you should not do final momentum minus initial momentum as some oranges, 5 oranges minus 4 oranges. Alright. It is a vector, it has a direction. So we need to use the vector subtraction. Vector subtraction in the sense you need to take the in account of the direction of the velocity. Okay, it might have changed the direction after some time. So according to that we need to what? We need to do the vector subtraction. We need to do the subtraction. Alright. So let us go to the law of conservation of momentum. What do you mean by conservation? Conservation means, this word conservation means something that does not change. Something that does not change. So we are talking about what? When the linear momentum is not changing. So when the linear momentum will not change, there will be some conditions, right? So there is a law that to be followed when we talk about the conservation of linear momentum. So what is that law? According to Newton's second law, what does it say? When there is an external force, there will be a change in momentum. That's what it sums up, right? If you have an external force, you have a change in momentum. So force is equal to mf, pf minus pi, that means final momentum minus initial momentum by time it took to change its momentum. So that is what does Newton's second law. Now we are concerned about conservation of linear momentum. That means momentum should not change. Momentum of the system. We are talking about the system. There may be so many bodies inside the system, but we are only concerned about the system, whole system. So if I am telling that momentum of the system should not change, when can it be possible? That means the velocity of the system should not change. When can the velocity of the system cannot be changed? That means I am talking about when the state of system should not change. When can the state of the system cannot change? If it is an isolated system. What do you mean by isolated system? That means your external forces on the system should be zero. There should be no influence of the external force on that system. Then you can have the what? Conservation of the linear momentum. This is qualitatively we have deduced. Let us see quantitatively. Now, in the absence of any external force, the linear momentum of a particle or a body remains constant. How is that? If f is 0, then p is constant, right? Let us see. F net according to Newton's third law is what? Delta p by delta t. Now we are saying this external force is 0, that means this quantity is becoming 0. That means what will be this? Delta p is equal to 0. What do you mean by delta p? Delta p is the change in momentum. Change in momentum is 0 means there is no change in momentum. That means if there is no change in momentum, which implies initial momentum of the system is equal to final momentum of the system because there is no change, right? We can also write as final momentum minus initial momentum is equal to 0, which implies P final is equal to P initial, that means initial momentum is equal to final momentum. This is the law of conservation of momentum, right? Momentum is not changing of the system. Everything I am telling, it is of the system. There may be so many objects inside the system. Their individual momentums of the objects which are inside the system may change. Alright, individual objects momentum may change, but the momentum of the system overall will remain constant under the absence of external force. Okay. I hope you have noted it down. If not, please pause here and note it down. So let us go further. So the linear momentum of the individual particles, what we have just said, can change, but the total linear momentum of the whole system remains constant. Alright. So if you think about something, see, you have a system. You have a system of, for example, you and your friend having 10 chocolates. You both form a system. You both are system of my interest. Okay, which means the chocolates which you are possessing are the system of my interest. Person A, you are having 1 chocolate and your friend is having 9 chocolates. So how many chocolates both of you together have? 10 chocolates. So the system of chocolates which you are having is 10. Now your friend may think that I am having more chocolates, let me give some chocolates to my friend, to you. So your friend gave 4 chocolates. He has 9, he gave you 4. So now after distributing the chocolates to you, after giving the chocolates to you, how many chocolates you both have? The 10 again. So now after giving, your friend will be having how many chocolates? 5 chocolates, because he have already given you 4 out of 9. Now you already have 1, he have given you 4, you are having 5. 5 plus 5 again 10. Right? Before giving also you are having 10, after giving also you are having 10. So what is the condition here? So you are not giving these chocolates to any other friend, because you both are my system. You both together form the system. Nobody is giving you chocolates and you are not giving the chocolates to anyone. Okay, you are distributing chocolates in between you. So distribution of chocolates in between you I can call as internal force. Alright, if somebody is not giving you the chocolates, if somebody is not entertaining you giving the chocolates, that means I can relate as there is no external force on you. Okay, so this is the basic analogy I can draw off. So what happens? Your individual chocolates may differ, right? Previously you have 1, now your chocolates raised to 5. Your friend had 9 chocolates, it reduced to 5. That means his individual chocolate distribution is changing. That means in analogy, our momentum may change, individual momentum of the bodies may change, but the overall momentum, overall chocolates are same. Okay, so this is the thing. So let us go and prove. This is a qualitative analysis. Let us prove how it is possible. So let us now take a scenario where you have a body A which is having a mass m1 moving with velocity u1. So there is another body B of mass m2 which is moving with velocity u2. So after some time they collided. After collision, they have changed their velocities. So m1 now is moving with v1, m2 now is moving with v2. Okay. Now this is after collision. This is after collision. So these two form our system. These two form our system. And no external force is acting on these two bodies. So the linear momentum must be conserved. So what is the initial linear momentum of this system? Initial linear momentum of the system is what? m1 u1 plus m2 u2, right? Now final momentum final momentum of the system is what? m1 v1 plus m2 v2. So this u1 change it to v1, u2 change it to v2 after the time t, after they get collided. So according to third law, you know that force on A due to B is equal to minus of force on B due to A. At the time of collision, what happens? At the time of every action has an equal and opposite reaction. So the force which is being exerted on B, the same force will be experienced by A in equal magnitude but opposite in direction. So this minus sign takes care of that opposite direction. Okay. So what is this force on A due to B? It is nothing but the change of momentum of A in the interval of time t. Okay. In some interval, let us suppose it changed its velocity from u1 to v1. In the same time interval, it changed the velocity of u2 to v2. Alright. So what will be the change of momentum of body A? It will be m1 into, what is the change in velocity? v1 minus u1 by delta t, that is equal to m2 into v2 minus u2 by delta t, and we should not forget to place this minus sign. Okay. So delta t will get cancelled. So if you rearrange this, m1 v1 minus m1 u1 is equal to minus m2 v2, minus into minus, plus m2 u2. Okay. Take this m1 u1 that side and take this m2 v2 this side. You will end up with m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So what does this part will give you? m1 u1 plus m2 u2, initial momentum of the system. Now what does this give you? Final momentum of the system. So initial momentum of the system is equal to final momentum of the system. So that is where law of conservation of momentum is valid, when there is no external force acting on this system. Alright, but we have just added these two. How we added these two? Because they two are traveling in same A and B are traveling in same direction. After the impact also they are traveling in the same direction. Alright, now let us take another scenario where two bodies are heading towards each other like this. See, this is before collision, m1 is going in this direction, m2 is coming in this direction, in the opposite direction to A. After collision, what happens? They are separating, they are moving away from each other. Before collision, they are coming towards each other. After collision, they are moving away from each other. So let us see. So suppose there are two objects A and B, this A and B, A, B, having masses m1 and m2, are moving with velocities u1 and u2 respectively. This is before collision. After collision, m1 acquires velocity v1. So after collision, u1 is changing to v1 and m2 acquires velocity v2. Unlike in the last example, what happened? After the collision also they are moving in the same direction, but here after the collision the velocity, the direction of the velocity is changing. So see, so rate of change of momentum of m1 in the time t interval is what? Rate of change of momentum in the time interval is nothing but the force. We are talking about the body of A. So it will be force on A due to B. Okay, rate of change of momentum of m1, right? m1 relates to A. So it is FB, FAB. When what is this notation? This notation FAB tells you that force on A due to B. Okay, and rate of change in momentum of m2 in the time interval t is force on B due to A. So according to Newton's third law, you know that these two are equal but opposite in direction. So let us go ahead and solve. So according to Newton's third law, FAB is equal to minus FBA, right? What is the change of momentum of body A here? It is nothing but final momentum minus initial momentum. If you take this direction as positive, this direction will be negative. So your final momentum will be minus m, if I have to be precise, m into minus v1, because it is in the negative direction. Final momentum minus what is initial momentum? m1 u1, okay, by some delta t time is equal to what is the change in momentum of m2, final velocity v2 because it is in the positive direction, minus of, because here u2 is in the negative direction, right? So minus of minus u2 by delta t. So what happens? This delta t gets cancelled out. Just solve this. This is m1 minus m1 v1 minus m1 u1 is equal to, here one thing we have missed again. We have missed the minus sign here, because this FAB is equal to minus of FBA. So take the minus inside. So it will be minus m2 v2 minus into minus plus, but it is already become plus. So it has already both together become plus. So minus into plus becomes a minus again. So m2 u2. Okay, redistribute this. So what happens? What we can do? Take, this is m1 v1, right? So take m2 u2 this side. So it becomes m2 u2, or otherwise you can do like this. So make just take m1 u1 that side. So it will be m1 u1 minus m2 u2. We are just rearranging to make you adjust and see where the initial momentum is equal to final momentum. Otherwise you will have to take more and more steps in the simplification. So that will be equal to, what is remaining? So m2 u2 is coming this side, right? So it will be m2 v2 minus m2 m1 v1, right? So what is this telling you? m1 u1 minus m2 u2. It is the initial momentum. Why it is initial momentum? See, m1 u1 is the momentum of the object A, and minus m2 u2 is the momentum of the object B. Why it is minus here? Because it is in the negative direction, right? Similarly, you can see m2 v2. v2 is in the positive direction, that is why it is having the positive value. Minus m1 v1. After collision, v1 is starting separating from v2. It is moving in the opposite direction, right? So that's why it is having minus m1 v1. So your initial momentum here also is equal to final momentum. You need to be careful while we are subtracting final momentum minus initial momentum. You will need to take the directions in consideration. All right. So here is our working. So m1 into minus v1 minus u1 by t is equal to the same thing what I have done, and we land up with m1 u1 minus m2 u2 equal to m2 v2 minus m1 v1. So this is the law of conservation of momentum in the isolated system. Initial momentum of the system is equal to the final momentum of the system. Okay. Now you can see that the individual objects' momentum are changing. m1 u1 was there before, it became minus m1 v1 after the collision. Here also the same thing. Before it was minus m2 u2. After the collision, it became m2 v2. Individual momentums are changing, but overall momentum, overall system's momentum is not changing. You can see initial momentum is equal to final momentum. This is the crux of this concept. Alright. Now, let us see how it works. Let us see an example. So, we have an example here where this is our system, truck and a car. You have the mass here, mass of the truck and mass of the car here. You also have the velocity. Before the collision, both are traveling with 20 meter per second each velocity. After collision, what happens? It stops, it goes back. See how the velocity is changing. Previously, it is traveling with 20 meter per second. All of a sudden, changed direction and acquired more velocity. It is traveling with minus 40 meter per second and it came to rest. If you just see its momentum, what happened? Before the collision, it is traveling with 20 meter per second in the negative direction. So, after the collision, it becomes 0. So, if you keenly follow, what is the change of momentum here? What is the change of momentum? What is the initial momentum? Let us see initial momentum of the system. Initial momentum. So, mass of the car 1000 into what? Initial velocity is traveling with, both are traveling with 20 meter per second, right? This is 1000 into velocity 20 plus what is the mass of the lorry, van or lorry? 3000 kg into the same speed it was traveling 20, but it is in the negative direction, so it is minus 20, right? So, what is this? So, 20,000 minus 60,000, right? 20,000 minus 60,000, what are the unit? Kg meter per second. So, that will be equal to your minus 40,000 kg meter per second. Now, after collision, what happens? This comes to halt, 0, and it acquires the velocity and goes in the negative direction. So, you already have, when it is moving, it is changing, minus 40,000. So, let us find final momentum is equal to 1000 mass of the car, 1000 kg into after the collision, what happens? It is moving with minus 40 plus 3000 kg mass of the lorry into it came to halt, it is not moving anywhere, so velocity is 0. So, it turns out to be what? Minus 40 into 1000, minus 40,000, minus 40,000 kg meter per second. Alright. So, you can see initial momentum is equal to final momentum. Why? Because there is no external force acting on the system, no cycloid, nothing is coming in between. So, these two form a system and they redistribute the velocity among themselves, between themselves. So, your final momentum is after the collision is equal to the initial momentum before the collision. So, that's it about this problem. The second one is the problem. I would suggest you to work this problem out by yourselves and you will get the habit of solving the problems in more accurately. In this, when we are talking about the Newton's second law, we have discussed that Newton's second law is the heart of the topic. Why? Because from the Newton's second law, we can deduce, we can go to Newton's first law, we can also go to Newton's third law and also solve the Newton's law of conservation of momentum, right? So, let us go to the first law. What the Newton's second law says? F net is equal to mass into acceleration, right? If the F net is 0, If the external force is 0, in the special case if the force external is 0, what I can think of? Mass cannot be 0, ma is equal to 0. So if this is 0, what I can write as ma is equal to 0. Mass cannot be 0 because mass is the matter contained in the body. It cannot be 0. It will have some magnitude. What can be 0? Acceleration can be 0, right? If acceleration is 0, what I will do? Acceleration is what? Velocity final minus velocity initial by t equal to 0, which implies that v final is equal to v initial. That means the object is traveling with the uniform velocity. That is what the first law is saying about. When there is no external force, there will be no change in the state of motion, right? So if there is no change in state of motion, there is no velocity change, there is no acceleration, that means there is no change of motion, there is no change in the state of motion when there is the absence of net external force. Alright, this is from the second law to the first law. We have already derived about the Newton's law of the conservation of linear momentum from the Newton's second law in the starting of this session. Let us recap that. So F net again can be written as what? Delta P by delta T. Again, if it is an isolated system, F net is equal to 0, right? So your delta P, this is 0, that means your delta P is equal to 0. That also tells that Pf minus Pi of a system is equal to 0, Pf is equal to Pi, right? That means final momentum of a system is equal to the initial momentum of the system. This is your proving the law of conservation of momentum from the Newton's second law. Now let us prove the Newton's third law from the second law. So you have a system here. You have a system here containing of body A and you have another body B. Okay, then you left it like this. This is the system of our interest. You left it like this and you went somewhere and you came back after so many years and you made sure that there is no external force on this system. After some years you came, you saw A is moving with some momentum and B is moving with some momentum, because there may be some internal forces between them. They acted on them. Then what happened? They were moving apart. And you found out this A is moving with momentum minus P, that means on this side, in this side. Okay. So when there is no external force, that means external force on the system is equal to 0. That means net momentum should be equal to 0. Net momentum of the system, net change of the momentum of the system should be equal to 0. Change of momentum should be equal to 0. That means if I need to make sure that total system's momentum should be 0, how I can make sure that total system's momentum can be 0? That means here I need not make sure. You can easily verify that if A is moving in this direction with minus P momentum, then you will definitely find out that B is moving with momentum P in the opposite direction. If you give in some time t, that means the change in momentum of body A in time t is minus P. If the change in momentum of body B is plus P, then they should be equal, right? Because they two need to add up to get 0, because delta P should be 0. If you are telling the momentum of A is minus P and momentum of B should be what? Plus P, so that it cancels out, right? If it is minus P, it should be plus P. So they might have interacted with each other with some force during some time. Alright, so that you can see that minus P by T is equal to P by T. What is this? Change of momentum in the time interval T. This is change of momentum in time interval T. Minus P is the momentum of what? Force on A due to B, and force on B due to A is P. That means change in momentum is P per time T. So I can write this as force on A due to B is equal to minus force on B due to A. This is what Newton's third law is. Let me summarize. You have two bodies. For example, you have the two bodies of symmetry situation, which I just talked earlier. They are approaching each other. You saw they are approaching each other. Okay. This is having some momentum. This is having some momentum. They are cancelling their momentum. They are coming towards each other. It is going with P. It is coming with minus P earlier. So what is the total momentum? P minus P. Initial momentum P minus P gives you 0. This is momentum of A. This is momentum of B. Okay. So they are in equal in magnitude, because I am telling it is a symmetry situation, right? So after some time, you came and saw they are moving apart now. Now they are moving apart after the collision. Now you saw A is acquired minus P, because it is a symmetry situation. If A is acquiring minus P, you tend to think not. You need to know that B will be moving with the momentum of plus P on the other side to nullify the effect of the momentum of the change in momentum of the total system. So that what happens? How much time it took to change that momentum? We just divide by time. The time will be equal because the two are colliding. Only two objects are there. So the FAB turns out to be minus of FBA. This is what is Newton's third law. So for second law, we can go to first law, third law, and Newton's law of conservation of linear momentum. So this is about your law of conservation of linear momentum. I hope you have understood this and enjoyed this session. So before going to the next session, let me give you some home assignment so that you can solve and get familiar with this topic. So the first question goes like, explain why is it difficult for a fire to hold a hose, fireman to hold a hose which ejects large amount of water at a high velocity. This is your first question. That means he is asking why it is very difficult for a fireman to hold a hose when there is a fire damage, the fire station, the fire engine goes no. So the fireman holding a hose, he has to hold the hose with high water, with more rigidity, right? Why is it difficult for him to hold a hose? That is the question. Our second question is, under what circumstances is momentum conserved? We have talked entirety of this session about this. So you have listened this properly, you can easily answer this question. Third one, can objects in a system have momentum while the momentum of the system is 0? This also we have discussed, and you have to explain your answer if you say yes or no. So this is about the law of conservation of momentum. Next 3 sessions we will be dealing with the questions on this chapter, which will be more interesting, and it will be more enjoyable too. So until then, thank you. Saira.